Yes. Good evening. I'm Alexey Gok. I'm running my own software engineering company in the little Swiss town of Schwyz. And today I'm going to talk about the project Arhat. That's our ongoing project dedicated to building a specialized neural network, specialized machine learning framework. One might ask, why do we need yet another machine learning framework, given that there are a couple of rather good and well-established and powerful software packages like TensorFlow or PyTorch and so on. The motivation for this development has been based on major recent trends in two important application areas. The first one is machine learning on the embedded platform, which becomes more and more popular right now. And on the embedded platforms, the common practice is to train networks using the traditional data centers and then deploy the trained network on the embedded hardware. And here we hit some issues and meet some challenges. And the challenges are that typically on the embedded platforms, there are substantial constraints on the power consumption, on the physical dimensions and weight, and also as the result on the computing performance on the hardware. And the hardware models which are used there are quite different. To make things more difficult, in many areas like avionics and automotive, there exists requirements for the safety certification. And safety certification requires that both the architecture of your hardware and software is open, and the software is substantially lean to be reviewed by the certification authorities, which basically makes it suboptimal or sometimes even not possible to deploy the system like TensorFlow, say, on the airframe and uses there for the neural network inference. The second trend comes from a completely different area. This is supercomputing. We are living now in the era where massively parallel supercomputing systems become ubiquitous. These systems typically provide a large number of interconnected parallel nodes, and every node has a heterogeneous architecture being equipped with the traditional CPUs and the GPU accelerators. It's also predicted that in the future, one of the most uses of these supercomputing systems will be for the artificial intelligence, and also these supercomputing systems will be integrated into the cloud platforms, effectively providing the supercomputing capacity to the cloud applications. Here we also see some problems because the traditional platforms, traditional machine learning frameworks, cannot very well scale to the large number of nodes. So if we need to parallelize our neural network processing to the big number of nodes, it's extremely difficult to do it with the existing platforms. So as the result, we are not prepared to meet the challenges, and we need some solution just because the existing machine learning frameworks are not well scalable. They cannot be well scaled down for the embedded systems. They cannot be scaled up to run efficiently and use efficiently the resources of the coming exascale supercomputing computers. As the solution, I propose building of the machine learning framework, which is capable of generation of lean executable code for the machine learning algorithms, which can do this generation for a wide range of target architecture. As one of the advantages, this will allow the direct embedding of generated code into the user applications, not requiring deployment of the large and complex machine learning frameworks on the target platform. And in case of the supercomputing, it would be possible to distribute generated code modules across several parallel computing platforms, just implementing the custom parallelization. So for the implementation, we have to note that there are basically two main implementation strategies for machine learning frameworks. I call them interpretation and compilation. Interpretation is the principle which is used by all the major machine learning platforms, in which there exists a large monolithic framework that takes on the input the description of the neural network model, and which itself interprets this description and performs all the required operations like training and inference. Alternative to this would be compilation, in which the framework takes the input neural network model and then generates the special code for every target platform. It can, in particular, generate the training code for one platform and then the inference code for the same neural network model for another platform. Here is the master plan for the project, which represents the final reference architecture. In the center of which there is an intermediate representation, which provides some uniform means to represent any neural networks in the standardized format. On the top of this, there is a front end, which provides the programmer with the application programming interface, allowing him to define the neural and specify the neural network. Behind, there are swappable platform-specific backends. At least we want to have the reference unoptimized C and C++ implementation, which is running on the conventional CPU. Then the backend, which generates the NVIDIA GPU code, which is a combination of C++ and CUDA. And we also want to support the AMD GPUs, which use a little bit different approach for the programming. They combine C and C++ with OpenCL and sometimes with the assembly language coding. Also, because in some cases we are not going to use our own front end for training, we can import pre-trained models which have been created using the external machine learning frameworks and then expressed in some common interchange formats like ONNX, and via the specialized software components, which we call bridges, import these neural networks into our system, just converting them to the intermediate representation. Well, that's the big thing which I want to have. Before embarking on this, I created, as the proof of the concept, the simpler machine learning framework, which provides only the basic NVIDIA GPU support. It contains of the engine, which provides both the application program interface, some kind of the rudimentary intermediate representation, and the engine, and is able to generate just two kinds of code, either unoptimized C and C++ reference code or the code for NVIDIA GPU. To simplify the development, I didn't want to build it from scratch, so I have chosen as a prototype an interesting neural network, an interesting machine learning platform, which is the Intel Nirvana reference deep learning framework. It has been implemented in Python, and basically Python is the standard language used in most machine learning frameworks, and this alone was the reason for looking for choosing some other programming language for the development. The choice was simplified by the availability of Go, which is an excellent programming language for doing such tasks. So while the prototype was implemented as the Python system working using interpretation as its mode of operation, our target was building the framework in Go, implementing compilation, generating C and C++ and CUDA code. So before I show how I solve this task, let's start with the description. Before we go ahead, we have to define the method for specification on the neural networks. Here is the example of the very simple textbook fashion neural network. It contains 4 layers. It's called MNIST MLP, and it's designed to classify handwritten digits from 0 to 9. It's implemented as the sequence of layers. Layers are processing tensors. Tensors are just this is just the slang word for the multidimensional arrays. So every layer here inputs a tensor, processes it, and outputs another tensor. So on the input of this network, we put the batch of say 120 images, if image is 20 by 20, if image is a grayscale matrix of 28 by 28 pixels. On the output, we want to get the one-hot representation of the result, which is a short array of 10 elements. These elements contain probabilities of the input image representing the particular digit. So if our network is trained well, we should get only one position close to 1 and all the rest close to 0. Some of these layers are parameterized. For example, fully connected layer, which does the linear transformation of the input tensor, holds weights, and these weights are actually parameters. If these parameters are set properly, then we get the correct one-hot representation. And the goal of training the network would be finding the proper weights. So now the takeout from here is just we have the neural network as a combination of the interconnected layers. Every layer represents a specific operation. Here we have just two operations, linear and activation. And the procedure of processing the input tensors is called the forward propagation. That's the most basic operation in the neural networks. Let's see how we define this neural network in the programming code. On the top, you see a small piece of Python code, Python code from the original Neon Nirvana. You see in the center there is a collection. There is actually the list of layers. You will ask why there are just 2 layers. We want 4. This is just because the affine represents a combined pair of linear layer followed by the activation. You see there is the activation reference there. In Python, there are used the keyword parameters. There is no such thing as keyword parameters in Go. So in Go, we just simulate this with the name-value pairs. For example, you see the n-out is equal to 100 and so on. So that's the way to define the models which we are using. Here is an example of a little bit more complicated model defined in Go. With more, this is the convolutional network, which consists on the top of 2 affine layers. We added 2 convolutions and 2 pooling layers. Definitions are always uniform. Every layer is parameterized by the key value pair. So concept is quite simple and quite similar to what you can see in the textbooks on machine learning frameworks which are using Python. To go ahead now, let's consider how we are going to train the network. To train the network, we have to add yet another operation which is called the backward propagation. It's actually opposite to the forward propagation we have just considered. And here the idea is that in the end of the forward propagation, we get some output. This 10, in case of MNIST, this is 10 element vector, which contains values which are supposed to be 0 everywhere except one. But if the weights are just randomly initialized, we most likely will get some completely different numbers. So we have some error in the output. We introduce the cost function. This cost function can compare the output of the forward propagation step with the supplied labels, generate the error tensor, and then this error tensor will be backpropagated to the top layer of the network. At every layer which is parameterized, the gradients for the parameters will be computed. So as the result, we will have along the parameters also the gradients. And then during the optimization step, these gradients will be applied and new weights will be created. Then in the iterative fashion, the weights will be computed to get the right result. Here is the general description of the training algorithm, also in Go. There are 4 main players which are shown downstairs, that's shown at the bottom. There is, of course, the model. Another important player is a data set, which is represented as an iterator. Every call to this iterator will produce a batch actually a micro batch consisting of a number of samples and number of labels. Then there is a cost function, and finally there is an optimization algorithm. So as you see, the training for a single epoch will be represented as a loop. Inside this loop, at every iteration, the dataset is queried to deliver a new micro batch. Then forward propagation takes place. We compute the result. Then we apply the cost function to compare this result with the labels and generate errors. Then these errors, which are named delta, are backpropagated. As a result of backpropagation, we get the gradients for the parameters, and then the optimization algorithm step combines the current weights with these gradients to get the new weights. So to implement these operations, we define the following architecture. First of all, there exists a front end, and the mission of the front end is implementing the API for which allow the programmer to define and process machine learning models. This API provides a catalog of different object types. There are, for example, many objects for the layers. Actually, we support more than shown here. Many variations for the cost functions, and many variation, for example, for parameter initializations and optimizers. On the other hand, we have the collection of swappable and platform-specific backends, and the mission of the backends is generation of the executable compute kernels implementing various machine learning operations, like training, which has been shown right now, or some lower-level operations like front and backpropagation. To generate the code, most likely, actually to make machine learning efficient, we will have to use GPU computing, which is kind of heterogeneous computing because it involves combination of conventional host CPUs with a limited number of cores, and devices or the GPUs which are featuring very large number of parallel cores and which are available to do computations in parallel by splitting jobs into large numbers of threads. Therefore, our generated code should be split in two parts. One part running on the host and implementing mainly the control functions, and the second part will be represented as collection of compute kernels. Kernels are running on the GPU, and every kernel will implement some substantial part of the computations. So our goal is to transform the model definition into a sequential host code, which will just be which will be responsible for all the input-output functions and orchestrations of calling the GPU kernels, and generation of the library of GPU kernels, each kernel implementing the specific operation, like, for example, computations, forward and backward computations for a particular layer, or some steps in the optimization algorithm, computation of errors, and so on. I just want to show some code. This, for example, the host code, which has been generated for the forward propagation for our MNIST model. There are 4 layers, and here you see just 4 steps which sequentially do forward propagation for different layers. For linear layers, I'm using the standard library provided by CUDA. For activation kernels, I'm calling the custom kernels, custom CUDA kernels, which have been generated just for this particular network. Here is an example of one of such kernels. That's a typical CUDA kernel. It has been completely generated automatically. You can see in the middle in blue there is actually the formula to which these algorithms corresponds. Arhat knows all this formula for different algorithms and is capable of translating this formula to the back-end code depending on the platform. So for the same formula, we can automatically generate code for CUDA and for CPU, for example. In the future, I will also able to generate the respective OpenCL code for AMD GPUs. Okay, that's generally how the system works. Now let me highlight how Arhat can be integrated in Elastic and how Elastic capabilities can be utilized in the real-life machine learning, distributed machine learning scenario. Basically, machine learning is all about models and data sets and manipulation with models and data sets. And Elastic is known as a very powerful tool for storing and manipulating complex and highly structured semantics information. And here we have two scenarios where we can use Elastic in handling, on the one hand, model descriptions, on the other hand, the dataset descriptions. Let's start with the model descriptions. As I will show in 2 minutes, any Arhat model description can be represented as JSON and therefore stored and managed by Elastic. So model descriptions can be fed into the Elastic database. We can create some high-level catalog which will annotate this model, so it will allow the user to discover to search and discover the available models. Parameters can be stored in some kind of blob storage, which is unspecified, can be perhaps any RDBMS. Then Arhat code generator, on the request of the user, can select the model description, generate the code, deploy this code on the target platform, and then this code can be run on the target platform, loading data from the certain, at this point, unspecified source. Here is just an example how our MNIST model can be described as JSON. So you can see here the familiar list of layers, definition of the cost function, optimizer, reference to a data set. On the top there are initializers, for example. So that's actually the format which can be used to store the model in Elastic. The second use case is data set management. Basically, in machine learning, management of data set is a separate area. It represents various challenges, and these challenges are just explained by, first of all, the large amounts of data, and second, the complexity, and second, of the variety of the formats in which data sets could be represented. So before we do anything, we have to ingest this data set that is represented in some unified format which is understood by our machine learning framework. Here again, Elastic can play a significant role because all the metadata during the ingestion process can be translated into some standardized form. The catalogs of these data sets can be created, and the respective images again will be stored in this unspecified blob storage, and then the user Arhat application can call the specialized component, which will the Arhat data loader, which will make the provision of data to the application. Of course, the structure of the meta information which will be stored in Elastic very much depends on the problem domain. There are different tasks. For example, if we just concentrate us on the image processing, there are two popular tasks: classification and object localization. In classification, the system is just supplied by the number of images. Every image has a single label, for example, whether it's cat or dog shown there. In the object localization is a little bit more complex case, where there are different objects on the image. For example, you can have a cat, a computer, a bottle of beer, and so on. So these images are annotated with bounding boxes. So here we should specify that that there are a couple of objects on this image, and every object is associated with its bounding box. Obviously, for the object localization task, we need the different representation. Generally, for different tasks, not just image processing, but for example, the audio or video processing, we can define the vocabulary, we can define different representations, and use this as the standard for keeping data in the Elastic search. So basically, that ends the presentation. My next intent is somewhere in the first half of the next year to make the proof of the concept implementation combining Elastic with Arhat, using some very well-known algorithms for image processing, very well-known image processing, very well-known data sets. Yes, so that's the next step. So I thank you, and Arhat can be freely downloaded on GitHub using this URL. Thank you.